Hello everybody and welcome to this virtual IGARSS also from my side. My name is Peter Baumann and I'm going to report briefly about some sideline of our work on array databases, that is query support for a large multidimensional arrays, using that in teaching environments and in different areas. So that is a little bit unusual. So where do we come from? We are working on what's called datacubes today, so function-rich services that work on spatio-temporally aligned and homogenized raster data assets. That there we encounter sensor data, for example, images, image time series, simulation output, and statistics data. Now this query language that we have devised for extracting information from such datacubes, actually, as it turns out, it allows combined teaching for several subjects, because actually these subjects get touched upon. And this feature of any query, anytime that a query language offers, actually allows students to do exploratory work. So what we have looked at is, on the one hand, of course, databases. So we look into a NoSQL query language as an example of declarative querying beyond table world, so relational databases. How could that work in a datacube setup? Second, analytical geometry, because as it's multidimensional arrays, we can describe such spaces and we can build high-level declarative expressions that describe fields, and so we can nicely visualize them as a query result. Finally, applying all that to geosciences on Earth data, we learn about spatio-temporal analytics and about the standards. I'm going to briefly present you 3 use cases now to illustrate a little bit further what that can mean. So let's start with Earth data analysis. There we find OGC WCPS, which is a high-level language standard that abstracts away from algorithmic aspects. That's good for students. No programming. So what can we learn there? We can work with extraction as the first thing. We extract data from some big data asset. We can do analysis of such data, and we can see results plotted and do an interpretation of them. So that allows students to simply write queries, and they can actually write such WCPS queries and enter them into interactive demos. You can see examples of that under standards.rustiment.org, and that actually allows then to suggest problems to the students. So what about expressing the NDVI? And then explain what you see there. But also students get encouraged to do own challenges, to maybe change the parameters a little bit, threshold the NDVI, or try out something completely new. Here's a sample query that uses this WCPS standard, where the red part resembles the NDVI, but we will soon find out when we want to display that on screen, we actually need to fiddle a little bit with the pixels so that we fit it into the 0 to 155 grayscale space. Okay, so much about that one. Going into abstract analytical geometry, actually, the rasterman query language allows to express such analytical geometry relations and functions. So it doesn't have to be functions, can be general relations. Here we would like to play with analytical geometry and get a better understanding. We can type in different expressions and see what that looks like. Okay, so we would do that first of all in 2D, of course, because this is nicest to display. And then again, people can play with that, and students get a few first hints and then can explore different functions of increasing complexity and can do their own thing. In this case here, we use in the select part of the SQL query an M-array constructor, which builds us a square of 501 by 501 pixels. The variables x and y are available to address this little coordinate space, and then we can, for example, draw a circle by having the squared, so power of 2 of x and y around the center of the circle, and that is what you would get then, unless you put a typo in the query as I did here. Okay, finally, going deeper in the stack, coming to databases. Here we find SQL MDA as a standard. This is an extension that deals with multidimensional arrays. Actually, it is the Rasterman query language, which you have seen before. So we encounter this one again. We do have declarative datacube queries, and that is something that students can explore in practical use cases. It's an example of no SQL, so not just tables. And in this case, we would go deeper and think about how can we do physical data organization, what impact would it have on performance, and so we can discuss about query optimization, for example. Again, it's about interactive queries, but then look into physical aspects, do timing experiments, etc. Run queries, for example, with and without optimization. Okay, here again we have some sample query. The red part is the array part, which extracts from some C, which happens to be average chlorophyll, and that is an object in the database. Actually, it's a table where we would extract array by array. We could get multiple results here, but I've depicted only one to showcase what it means. And then we can do such statistics, which actually would get us back a one-dimensional diagram as displayed here. But as this table can hold multiple arrays, you could get a series of results here. Okay, I cannot go into the details of the language, but maybe it showed how we can go into different subjects and do the same thing and actually combine different students, students from different areas, and possibly team up. Declarative array languages give us an aspect, a flavor of interactivity, allows to generate functions and relations and visualizations of those, and actually has turned out that for students it's really fun to connect to that. Database students like the idea that they suddenly can work with satellite images. Acknowledgement, there has been earlier work that was a great collaboration with Claudio Bausa Medeiros from Universidade de Campinas. And actually, I would love to continue that with some colleague who's interested in devising that into some course material and then doing some paper about it jointly. Okay, with that, thank you for your attention and wish you a great IGARSS for the remaining days. Bye-bye for now.